In this final chapter of the series on artificial intelligence and its geography-related applications, we will look at the theory behind recurrent neural networks and its implementation on weather data. So far, we already know how to make ANN regression and classification models and how to set up and train a CNN for a classification problem. But all the models we have seen so far are not able to put data into a temporal context. And by data with temporal context, I mean sequential data for which the order of information really matters. Like texts where the order of words in a sentence is crucial to understand its meaning, or films which only make sense if we put the individual frames into the correct order. And of course, time series data like sequence of satellite data or weather data. Recurrent neural networks, or RNNs in short, have the capability to kind of remember previous inputs, which gives them the possibility to identify temporal relationships in our data. When you dive into RNNs, you will sooner or later stumble across the different types of RNNs. The first type is a simple one-to-one network. The green box illustrates the input vector. The middle pink block illustrates the RNN state, and the blue box the output vector. A one-to-one network is just a vanilla neural network and is not often used in an RNN context, as we do not really profit from temporal insights. However, it can be used for image classification. Then one-to-many, where we have a sequence of outputs. This architecture can be used for image captioning or audio generation. Then many-to-one, where we have a sequence of inputs and want to have a single output. This can be used for sentiment classification of an audio, film, or text. Or we have a time series of satellite data to make a statement about vegetation health. Then we have two types of many-to-many architectures, which have a sequence input and output. One for use cases in which input and output should have the same size, like named entity recognition, where the model tries to pick out specific words from a text. Or you try to classify a drought risk for each day in your weather data. The other one is for use cases where the input and output sequence might have different lengths. This could be language translations, where the translated sentence might not have the same length as the input. Now let us have a look what gives an RNN the capability to remember information from previous time steps. First, a simple perceptron, as we already know it from the ANN lectures. The calculation is very simple. We have our input x, which is multiplied by a weight w, we add a bias term b, and put the result through an activation function like the 10H or sigmoid. RNNs use a loop to retain information from previous steps. So the output of the first time step is also an input for the next time step. When we talk about RNNs, we always have to talk about the hidden state. The hidden state can be understood as the output of an RNN unit, but it is so much more than that. It is a memory that stores information from previous time steps to help the network process sequential data. To put it into a mathematical perspective, this means that we do not only have our weight and bias for our input data, but we also have a weight for the previous hidden state. So WH times H of t minus 1. This additional weight WH controls how much the previous hidden state influences the current hidden state. Note that WX and WH are constant throughout the time steps, meaning the same weight matrices WX and WH are applied at each time step. Let us illustrate the hidden state graphically using temperature data. We have a sequence of 5 days of temperatures. Now the RNN should predict the temperature for the 6th day. The RNN will look at one observation at a time. So it takes the temperature of the first date and produces an output. In the next step, we not only feed the temperature of the next day into the RNN, but also the previous hidden state. So the hidden state of the current RNN unit also holds the previous hidden state. In the next step, we again provide the temperature data of the next day and the previous hidden state, which itself holds some information of the very first hidden state. So the current hidden state always inherits the previous information. And this principle repeats itself over a user-defined length of data, which is in our case 5 days of temperature data. The output of the last time step will then be the prediction for the 6th day. What we just did is to unfold the looped representation of the RNN. You will often read that the RNN can be unrolled. So you see that an RNN is nothing else than a sequence of identical neurons with identical weights which are just fed previous information. Let me quickly simplify the illustration a bit. Now, the fact that those are identical weights and biases in the RNN unit gives us some serious problems. I hope you remember the concept of backpropagation from our previous lectures. In short, backpropagation is the process where the error from the output is propagated backward through the network, layer by layer, to update the weights based on how much each neuron contributed to the error, and thus optimizes the model's performance. Now, the problem is that we need to backpropagate through all time steps of the RNN unit. And if we had 50 instead of 5 days of temperature data under identical weights of, let's say, 0.5, we would repeatedly multiply the error gradient by 0.5. So we multiply the error gradient by 0.5 to the power 50, which results in super low gradients. Those very small gradients lead to very small adjustments of the weights and biases, which means it will take an eternity until we reach an optimum. On the other hand, if we had larger weights of above 1, our gradients explode and the model will always overshoot the optimum. Thus, we also speak of vanishing or exploding gradients. There are several solutions for this problem. One option is to clip the gradients to a specific value range, so they cannot get too small or too large. Then there is weight normalization, where we divide the weights, for example, by the L2 norm and add a learnable parameter, improving training stability by separating the magnitude and direction of the weights. Then we could apply truncated backpropagation through time, which means that we do not backpropagate through all time steps and thus reduce the risk of vanishing or exploding gradients. However, all those options only treat the symptoms of the problem and not the problem itself. Thus, I want to mention two solutions that actually take care of the problem: gated recurrent units and long short-term memories. Gated recurrent units, or GRUs in short, and long short-term memories, also called LSTMs, have gating mechanisms that allow them to selectively retain or forget information from previous time steps. In general, GRUs are simpler than LSTMs as they only have two gates. The update gate controls how much of the previous hidden state is carried forward to the current hidden state. The reset gate controls how much of the previous hidden state to forget. In other words, it determines whether the previous information is relevant to the current time step. LSTMs are a bit more complex. They have three gates: a forget gate, an input gate, and an output gate. As we are going to use LSTMs later in the hands-on lecture, we should discuss them a bit more. And this is how an LSTM cell looks like. This might look a bit overwhelming, but don't be afraid. It is not that complicated and we will walk through it step by step. First, I want to focus on those grayish arrows at the bottom. They illustrate the input that comes from our data. Only one observation, aka time step, is passed into the LSTM cell at a time, which does not mean it cannot be several features like temperature, humidity, and wind speed. But let us just feed the temperature in the LSTM to keep it simple. The input gets a weight at each point where it flows into the LSTM cell. Then we have those green arrows, which is called the cell state and represents the long-term memory. As you can see, there is only a multiplication and an addition, but no weights. Thus, the long-term memory cannot suffer from vanishing or exploding gradients. In such a single LSTM cell, the cell state can be represented as a single vector, which carries information over long sequences of data. This vector can be modified by the aforementioned multiplication and addition, so a different long-term memory can be passed to the next time step. I will leave the name of the long-term memory in the top corner as we will need it later on. Let us now concentrate on those pink arrows. This is the hidden state and represents the short-term memory. Unlike the long-term memory, the short-term memory has got weights. But its primary purpose is to transfer information only to the next time step or to provide the output of the LSTM cell. Just like the cell state, we can represent the hidden state as a vector as well. As we just have a single LSTM cell, this could be a single value. Let me also note the short-term memory in the lower corner. After we have discussed the input, the long-term memory and the short-term memory, we can now talk about the different gates. And start with the forget gate. First, we sum up the weighted input and the weighted short-term memory. Then we push the result through a sigmoid activation function. And the result of that will be multiplied by the long-term memory that comes into the LSTM cell. So if we had an initial long-term memory of 2, and the output of our forget gate is 0.997 after the sigmoid, we get an intermediate long-term memory of 1.99. As you can see, the forget gate decides about the proportion of the long-term memory to be remembered. And even though the forget gate looks pretty fancy, in the end we just weight certain inputs, sum them up, and put an activation function over it, which is what a simple neuron does. So it looks fancy, but it is simple. Let us move to the input gate. The input gate consists of 2 parts, and I will start with the right one. Again, we just sum up the input and the short-term memory, which have got different weights than the forget gate, and push the result through a 10H activation function. That means that the output can be positive or negative. This represents our potential change of the long-term memory, at least if there wasn't the left part of the input gate. This one uses a sigmoid activation function and decides about the proportion of the potential change what is actually added to the long-term memory. So the input gate determines how to update the long-term memory. If we put this into some numbers, the right part of the input gate could have produced a potential change of 0.97. And the left part determines that 60% of that value is kept and passed to the long-term memory, resulting in a new long-term memory of 2.57. Let us now come to the last part of the LSTM cell, which is the output gate. It also consists of 2 parts, but this time I will start with the left one. It has a similar purpose as the left part of the output gate and determines the percentage of the new short-term memory. Notice that this part also has its own weights for the input and the incoming short-term memory. In the right part of the output gate, the potential new short-term memory is calculated from a 10H function and gets multiplied by the calculated proportion. The result is the new short-term memory. This is the only part where the long-term memory takes influence on the short-term memory by passing the updated cell state through the 10H function. If the new long-term memory was 2.57, we would receive a potential short-term memory of 0.99, which we then multiply by the proportion and receive a new short-term memory of 0.98. If this was the last time step in our sequence of data, this would also be the output of the entire LSTM cell, which is the reason we call it output gate. Now we have discussed all parts of the LSTM cell, but how does it look like when we pass a sequence of data through it? Let's assume that this graph holds the data we want to push through the LSTM cell. The first 4 data points are observations we want to feed through the LSTM cell and predict the 5th value, which is highlighted reddish in the graph. Now the first observation of the data sequence is passed as an input into the LSTM cell. The initial long and short-term memory are usually initiated with zeros for the first time step. Under those inputs, the LSTM cell generates a new long and short-term memory for the first time step. Those will be the input memories for the second time step, for which we then select the second observation as an input. The LSTM cell again produces updated memories for the next step, which takes in the third observation, and so on, until all observations of the data sequence have been passed through the LSTM cell. The hidden state or short-term memory of the last time step is then the prediction for the 5th time step. Of course, the length of the data sequence is something that we decide, So we also could have had 20 observations. This is the end of the theory lecture about RNNs and LSTMs. In the next video, we will set up a simple LSTM model to predict the temperature of the next day based on weather data from the past days.